So I want first to thank the organizers for inviting me at this seminar, and especially LCO. So I will present my presentation. It's on experimental identification of transfer functions in the case of diffusion or advective heat transfer for a special type of system, linear time invariant dynamical systems. So my lab, LEMTA, which is an engineering lab mainly on mechanics and energy, is located in Nancy, in the eastern part of France. Nancy is a city very famous for its old 17th century square. So as LCO told, my main topic is experimental inverse heat transfer problem in engineering. And recently, I got an interest in convolutive models and their associated inverse problems. So some applications we did are very diverse. For example, pollutant source identification in a ventilating domain, where the domain is airflow. And we have a turbulence, and we made a transient concentration measurements in order to retrieve the pollutant source in terms of grams per second. Another application, it's one of my colleagues, now a former PhD student, works on heat exchanger for transient thermal behavior with a contract with industry. And more recently, we work on virtual sensor construction in a furnace under vacuum condition. It's a PhD of Thomas Lussouarn with a cooperation in Safran with radiative heat transfer, but which can be also linearized. So my presentation will include 4 parts. First, I will we'll have some part on modeling for linear time invariant systems. Then I will consider the calibration problem in the case of a heat exchanger with experimental inversion. And then we'll have a special analysis of the specific deconvolution deadlocks. In the last part, I will spoke about rectangular deconvolution. So let's assume that we have a material multi-component system. For example, it can be composed of a capital K solid or fluid domains here. So you have a domain with boundaries. You have a solid here, and so on. And in between, you can have fluid flows. And the assumption we make is the thermophysical properties of the subdomains, either solid or fluids, do not vary with time nor with temperature. They are constant in time. And also, we assume that we get a steady velocity field, which means that velocity doesn't depend on time, but it can depend on space, of course. So now we assume that initially we have a uniform temperature field. That's the easiest configuration. Or we can have a steady state temperature field. And we assume also that there is only one single separable thermal excitation, which can be a product of a time function and a space function, a space support. And so you can have, for example, a volumetric heat source, QV of T, inside the domain. You can have a surface heat source, QS of T, or you can impose the variation of the temperature on the surface, so it's temperature source. We can have also a change of, here you can see that we have H coefficients on the boundary. We can get a change of the initial fluid temperature that departs from its initial value. Or we can also have, and that's the case for heat exchanger, a change of the inlet temperature of one fluid. So there is a change of the enthalpic flow entering the system. So, in all this part, the separable excitation in space, it can be a point excitation, a line excitation, a surface excitation, or a volume excitation. So now, as a consequence of one of these excitations, you will get a transient temperature field and developed at any point in the system. So if we call U of t one of these excitation, you will have, for example, a point response at any point. We'll call it y. So I recap. We have a physical system, a set of solid and fluid, 3D, possibly 3D forced convection with constant velocities in time, but not in space. And P is any point in the system. So the single thermal excitation is defined by its support. Here we consider the case of a volumetric heat source. So since we consider the transient heat equation, with also which is written here, boundary conditions that have time invariant coefficients also, and for example, uniform initial temperature field or steady state. So in this case, the system is said to be linear with time invariant coefficients. So here we have the transient term, here with possibly varying volumetric heat capacity with the location. Here you have the advection term with possibly also with the same volumetric heat and possibly varying in space local velocity. Here you have the conductivity that has not to be uniform. And here you have the source. Here you can see the separation property. You have the intensity, QV, which is here. And here you have its support, F of P. And here you have the volume of the source. So as a consequence, at any point of the system, the temperature will rise. And we will consider only the variation of the temperature at some location with respect to the initial temperature exactly at the same location. If we have a steady state, it will be the local steady state value. So what we'll do, we'll Laplace transform this temperature. So Laplace transform, we use a bar, and of course, you will change the time here and here into the Laplace parameter P. And in that case, what happens is all the terms here, they are linear in time, so you have the time as a product, so QV of t becomes QV bar of P. That's a Laplace transform. Same for the temperature, because all these operators, they commute with the Laplace transformation. Here you have the advection term. The only different transformation occur with the transient term. When you transform a derivative in time, you recover P multiplied by the temperature minus the initial temperature. But since we use theta is equal to 0 initially, you have only this term. What is very nice here is that now you add a PDE, now you have an ODE, an ordinary differential equation, and as a consequence, you have only, I don't list the different, here you have a volumetric heat source. If there is no volumetric heat source, this term is equal to 0, but in the boundary condition, one of the equations have another excitation, so it's exactly the same. So what we say, because it's linear, we know that any temperature theta bar, the Laplace transform, is proportional to Q bar V. And it's true for the temperature, but it's true also for its local gradient. If we integrate on a surface, it's also true for example, the flux, the rate of heat flow exchange with the fluid. everything is proportional to the source, QV bar. So in that case, we can write the response at any location in Laplace space as a coefficient, which is the Laplace transform, multiplied by the transform of the excitation. It's a simple product in the Laplace domain. So so what is u of t, the original of the Laplace, the inverse Laplace of u bar? It's, for example, the variation with response to the initial, if you have a steady state initial field, and this is 0 if you start from equilibrium. It can be a variation of the surface temperature. It can be a variation of the fluid temperature. It can be a variation of the inlet fluid temperature. So you have the original, the inverse Laplace transform of h bar is h of pt. And as a consequence, the response in any specific point it can be local temperature, local heat flux, rate of heat flow over a surface. So now if we return to the time space, the simple product here becomes a convolution product. So you get here a convolution integral with integration. We are in time, so it's not between 2 points, but between 0 and t at the same time t. And so we can, we have considered the different types because we need a vocabulary to differentiate, to sort these different transfer functions. If we have a power source in watts and the response is the temperature difference in kelvins, we call this transfer function H. It's an impedance. If you have a temperature difference, for example, this one as input and a local temperature as an output, we call it, there is no name, we can call it a transmittance. If it's a power source, Q in watts here, and a rate of heat flow, for example, on a surface, it's also a transmittance. Transmittance have in hertz, the inverse of seconds. And if the excitation is temperature difference and the response is a rate of heat flow, using exactly the same vocabulary as in solid mechanics or in electricity, we can call it an admittance Y. So here is the equation. Here you have an example of excitation, transfer function, and response. There is a very interesting property of this transfer function is that when you integrate the transfer function between 0 and infinity, for example, here you have the transfer function, you assume you know it, you make the integral, it's exactly the ratio between the steady state response and the steady state excitation. For example, here we know that at steady state we'll get an asymptotic constant level. So it's very interesting because using the transient regime you can get property about the steady state regime. For example, in heat transfer in engineering, very often we write on a flux pipe we write T in minus T out between two isothermal surfaces which are connected by a cylindrical insulated surface. We call it, there is a flux, and we call this quantity a resistance. Here, when we do that, it's also a temperature, a general resistance, if you want, but it's between the steady state value and the initial value, or the equilibrium value, or the external external medium value. And here you have the excitation, so it's exactly the same. So as I told you, U can be a thermal power, Y a temperature variation, and in that case, we denote Z as the impedance. So now we'll go to an application. And we consider a heat exchanger. For people not familiar with the heat exchanger, you have in this simplified sketch, it's exchange of heat between two heat flows. Here you have a cold inlet flow going this way. you have 2 walls, and on the other side, there is, for example, in the other direction, a cold fluid going there, and the objective is to transfer the highest possible level of heat from the hot fluid to the cold fluid. So it's, you have 4 inlet-outlet points, inlet of the hot and cold fluid, and outlet of the hot and cold fluid. So the assumption is that to apply these impedances, for example, is to apply that all the properties, the coefficients, do not vary with time. For example, the velocity do not vary with time for the hot and cold fluid, and also for all the different coefficients. But it has not to be developed dynamically, whatever, it has not to vary with time. We have either uniform initial condition or initial steady states. We consider the heat losses through convection or linearized radiation with the external environment through a constant heat transfer coefficient. And here, in this case, we consider only one temperature source. We suppose that T4 is equal to T infinity. So theta 4, which is the difference between the local temperature and the initial temperature, is equal to 0. So we only have this excitation. We change the temperature of the entering fluid. As a consequence, the relative temperature at any point of the system will vary. Of course, for negative point at any point PQ, for negative time it's 0, and then it's different from 0. So we have this system. We have the response at any point, the transmittance, and we call it a pseudo source. I'll explain later why. And so at a given time, now we sampled this convolution product. So at a given time and at a precise location, we make a quadrature. We use the step size, the acquisition step time here. And we just have to make the average over each time integral. For example, here, we have, at any location, we consider the sample value. It's a point value at a given point, but for the temperature here, it's an average value for the theta 1, which is here. So for either W, the transmittance, or for the pseudo source, we will consider the average over the discretization time. So one simple way to calculate this average is just to sum the local sampled function at 2 adjacent times. So we have the excitation, you have the transmittance, and you have the response at the different location. So what is nice with this scalar quadrature, it can be given a matrix vector form in discrete mathematics. For example, here we have the response, which is discretized at each location in the heat exchanger. It can be a point in the fluid or in the solid, whatever. And but for the transmittance, W, we use the local average value, and the same for the excitation. And so for when you can introduce, so the previous scalar value can be transformed into this vector equation. And here you see a very special type of matrix. It's a lower triangular Toplick's matrix. What is nice, it's formed only with the argument. Here, for example, if I consider M of Z, you have the Z1, Z2, and so on, and you just move by one line, and so on. So it's triangular. So one vector gives birth to to a square matrix. And what is also nice is that we can, this product can commute. So you can write it because you know that a convolution product, it's a commutative operation. So it can commute, and you can use here, the matrix of the discretized transfer function. And don't forget here, it's very important to put the delta t for homogeneity reasons. So in the first experiment, we measure theta q, we measure the pseudo source, we have to solve an inverse problem, and we estimate the transmittance. So it's an identification inverse problem. And in next experiment, you know the transfer function. So you measure, in another experiment, you measure the output, and you try to recover the input. So it's, for example, it's a source estimation problem if theta 1 is a source, which is the case here, or it's a virtual sensor inverse problem if we want to recover the temperature at a point where it's impossible to make measurement in the situation, in the experiment of interest. So we have a model for the identification calibration problem. So when it's here, you have exact value. But when you make measurement, there is noise on the output and on the input. So if you use ordinary least squares, you can formally, without noise, you invert this matrix. But since the problem, there is noise in both input and output, it's an ill-posed problem, so you need regularization. Here we use either truncated singular value decomposition or zero-order Tikhonov using discrepancy principle. So here it's an example. So here that's the heat exchanger, and here we use heat source because a power heat source because it's easier to control. So that's the real cause, that's the real source. And using an impedance, you go back to theta 1, T1 minus temperature, initial temperature, and you have an impedance. And since this point is before this point, for example, in the wall, it's a pseudo source of the elevation of temperature, either in the wall or in the fluid. So between these two temperatures, theta 1 and any location, theta p, you have a transmittant. So here it's the box scheme, an impedance here, a pseudo source, a transmittant, and temperature elevation at any location. So now it's an experiment. It's Wasim Al-Haddad, I forgot to mention, which is a former PhD students in my lab. He did the experiment. You have here a small channel. You see the dimension with 1 millimeter channel between 2 millimeter walls on each side in polycarbonate. So it's not an heat exchanger, it's a half heat exchanger because there is only one flow. There is an inlet truncization chamber here, fluid flow, and it goes here. Here we put a small heating resistance and very small thermocouple here and here. So here you have the impedance, and here between this point, the source, and this point, between this point, the source at this point, and here you have the transmittance. And so we made measurements. That's a measured value. So we use first a step excitation, and here you have the measured temperature at the inlet and outlet. And here we use a different type of excitation with a square periodical heating, starting from 0 at thermal equilibrium. So here you have the impedances that were identified in both experiments. So they are very close. We use here Tikhonov regularization. And what you see, for example, here, they are exactly the same at the inlet, but at the outlet, there is a small difference. Why is there a small difference? Because we noticed in one of these experiments, there was some air present here. So the system has changed between the two experiments. So if the transfer function change, it can be used as a non-deductive testing of a variation of something in the system. Otherwise, they should be the same, because what is the interest with transfer function? They are independent on the excitation that give birth to the response. So now we did the same. We tried to measure the transmittance between the two temperatures. We use either truncated singular value or Tikhonov for step excitation, for periodical excitation. It was a little less nice than in the first case. You got excitation but globally, it's the same shape. You have transmittances are always the same. They go from 0, a maximum, and then they go back for a longer time. So it's more difficult to estimate transmittance because you have both noisy output and input than impedances, because here you have a good power estimation. So now we make a zoom on this problem of deconvolution to see the different deadlocks. So we took a simpler case where it's pure diffusion between a front face and a rear face of a slab. Here you have the heat equation. You have you excitate by the front face using a heat flux, and we have heat losses H coefficient with the environment here. Initial time, we have equilibrium, theta equal to 0, because we make a change of variable. And we are interested by the transmittance between front and rear face. So here you have W as the transfer function, theta 1 front face and theta 2 rear face. You Laplace transform the problem, and what is nice is that you get an analytical expression for the operational transfer function in a Laplace domain, which is given here. You have the H coefficient here, you have the thickness L of the slab, and you have here the Laplace parameter and the thermal diffusivity. You have hyperbolic sine and cosine functions in the solution. So what is nice, it's possible now to make numerical inversion of the Laplace transform. Now you have a nice software packages that make it in a good way. We use Hooke's algorithm to recover the shape. And since we have the time shape, we can use now any excitation, but now it's a temperature excitation, and we took an exponential excitation, starting from going back with a steady state value for infinite times. And we wanted to calculate, without noise, the response. Here we used, in order not to commit an inverse crime, we plot the analytical W, and we calculate the front face and the rear face temperature using COMSOL. And so we used the inversion of the Toplick's matrix. And we got exactly, using either ordinary least square or total least square, I will talk a little later about it. Without regularization, we got exactly the same transfer function. So now we have, in the real world, we have noise. We have noise on the output and on the input. So if we have noise, and since this matrix is noise, because U is for example, this function, it means that the matrix here is noise. So there is a noise in the matrix, which is more difficult. So in this case, the people that make linear inversion with a noise, matrix operator, they use total least squares. What is the total least square? You use the original square matrix, and you make a concatenation with the output. and we call G this matrix, and you minimize the transfer function to have a minimal residual of both the output and of the input. In this case, it's possible to make a matrix residual using the Frobenius norm. So I don't detail, but here this inverse total least square problem is ill-posed. So we write it in the SVD form. We make a truncating singular value decomposition to make it regularized, and we get, using some manipulation, we get the estimation of the transfer function H. So here are the results. So we put some noise to the preceding input, and we kept zero noise on the output, while you have the exact analytical, and you have, using either OLS or TLS, totally square, you have nearly the same estimation, which is very good. There is no much difference between, and the zero level is nearly conserved. So now we make the opposite. We noise the output and not the input. And in this case, it's not as good. You have oscillation here, and you have also a shift of the maximum. So in this case, we had a noise over signal ratio of about 4% using L2 norms. So if we put noise on both temperature, it's even worse. And you see that here we depart from the zero level oscillation, and so it's not as good. As a conclusion of this first part, this comparison, we can say that the noise on the response is more penalizing than the noise on the excitation, on the source. The truncating total least square technique is not really interesting because it doesn't take into account the convolutive structure of the Toeplitz matrix. So there is no improvement of the estimate. And it's very important to improve the short time value of the identified transfer function in a calibration experiment because it has the largest impact on posterior inverse input estimation experiments. So I just talk a little about rectangular definition. Here you have the calibration problem. In classical linear inverse problem, you have M output and N input, which are the unknown. What we did right up to now, we have the same number of unknown as measurements. And so we are very greedy. We have, so is it possible to be more parsimonious? So if you are more parsimonious, maybe it would be easier to estimate the data. So, and what we will use the parametrization of the transfer function. So the idea is to tailor the definition of the estimate. So in order not to have a square problem, but we have to have a rectangular inverse problem, so to have less many unknowns than data. So the calibration, it's a model identification for a given structure. Here we have M output, noisy data, same for the input. We have a reduced model structure. Here we will try to get rectangular parametrization using piecewise constant parametrization for W. You can have another structure, for example, ARX models also give you the same type of reduced model. And if we have parameterized these two functions, piecewise constant function of n parameter and the original sample value for the output. We have regularization, and then we'll get the estimate. So, 5 minutes, yeah. So here we track the singular value of m of theta 1 with noise and without noise, using theta 1 either as sampled or either as integrated over a time step. So you see here, there is a zoom here. You see that with noise, there is a difference. When you have the 10th singular value, here we had a big number of measurements. And we saw also that, so with noise, of course, the singular value drops. And without, when you use the sampled, so the initial, the first singular value doesn't depend on the type of parametrization we make, or neither nor on the noise. But the condition number with the stairs function is worse than with sampled function. Here you have the effect of the truncation with so no, here there is only noise in theta 2 now. So we keep the same input, but we modified we put noise on the output only. And that's the discretized one in blue, that's the right one, but discretized on the 0.5 seconds time step. And here you have either the function W on stair basis, on stair parametrization, or on point values. You see, the bias is a little better for stair parametrization with respect to sample value. So rectangular deconvolution. So the initial grid is this one, time grid, the grid for both the data and for the unknown. And we say, well, we'll take a larger time step and we parameterize on a wider grid. So here, so what we do, n is smaller than m, and of course the ratio we choose an integer. So we have the square model here with a topic matrix square here. And what is nice, when you do this process, you make an average, a surface average of these, for example, 3 levels. So in this case, when you see the vector of the sensitivity matrix, the nu is still linear when you are rectangular, but each column vector is the average of the corresponding, for example, 3 vector of the original matrix. So in this case, what you do is that you correlate a little more the sensitivity, but you give more weight to each of them. So here we use here it's no noise, and now it's a rectangular. Instead of 1400, we use only 87 unknown. So there is not much difference. The RMS residual is the same. Okay, so no gain in terms of estimation bias. So we check the length of each sensitivity vector in the square case, in the rectangular case here. And you see the problem here is when you have a sensitive vector which is close to 0, it makes the problem ill-posed, because when you have a free set when you have you know that if in a set of vector 1 is very small in terms of length, you know that you have no free set anymore. So that's why maybe it's better to give more importance to the last step. That's what we did here. We took, because here we got steady state on the output. We put a steady value, and we say, well, so we have only 51 sensitivity coefficient, but they are not uniform anymore, because so here is the results in red. You see that this part is not too good, but at the beginning there is an improvement. Here it was with 87 equal time steps, and here you have the non-uniform time steps. So there is an improvement in this part of the transfer function. So my conclusion: we have seen the importance of the transfer function and the way they can be used. What is interesting, they have a commutative vector matrix form in discrete time, so it's a very interesting model to use. Of course, it's not very used by engineers. Why? Because it's you know that inverse Volterra problem solution is an ill-posed problem, so that's why it has not much success up to now. So you have first an identification problem with calibration first, and then we can use a source estimation problem, virtual self-sort problem, or use in a non-destructive testing procedure next. What is interesting about rectangular deconvolution is you have a pertinent way of tailoring your unknown parameters. And the perspective, as I told you, is to work on IRX structures that can have a link with transmittance. Thank you.